Okay? One more thing to talk about here. You've got now a table of standard reduction potentials. Okay? And there is an important word in the title of that. The word is reduction. Look at that list of chemical reactions. Or, if we're going to be more precise, they're half reactions. What do all of those things have in common? In all cases, they involve the consumption of electrons, don't they? Every single one of them involves the consumption of electrons. Well, in a galvanic cell, you're going to have only one reaction that does that, aren't you? Because the other one has to produce it. It has to be the oxidation reaction. So how is this table useful for oxidation reactions? It's useful if you know that for an oxidation reaction, first of all, an oxidation reaction is the reverse of a reduction reaction. So what you can do, find one of these that is the opposite of what your thing says it should be, and just turn it around. Now, when you reverse the reaction, what do you suppose happens to the fancy E value? No?
It's 0.52 52 volts.
Nope.
1.5.
Nope.
1 over 0.52.
Nope, but you're getting closer.
0.5.
Negative. Okay? If you reverse the reaction, you reverse the sign on fancy E.
What's the relationship between fancy E and volts?
Fancy E is volts.
One what?
Volt is the unit of measure for fancy E. Just like the unit of measure for delta G is kilojoules per mole.
So electromotive force and electrical potential are the same?
Yes, they are.
Oh.
Two different ways of saying the same thing.
Okay.
Okay? If you reverse a reaction, change the sign of fancy E. Okay? Is that enough for one day?
Yeah.
Okay.
I have to agree.
So, let me put up a few homework problems that you can probably start working on now. This is chapter 17. Okay?